Hey everyone, welcome to this explainer. Today, we're diving straight into the modern, computer-aided tools that literally shape the world around us, land use planning. I mean, if you've ever looked at a city and wondered, how do the roads, the parks, and the residential zones all fit together so perfectly, or, let's be real, sometimes not so perfectly, well, you're looking at the results of this exact discipline. So let's explore the incredible technology that makes all of this possible, specifically Geographic Information Systems, or GIS, and remote sensing. Here's the agenda for today's explainer. First, we'll cover maps and mapping basics. Next, the applications of GIS. Then, map overlay analysis. And finally, the applications of remote sensing. Okay, let's dive into this. How do we know exactly where a city should expand next? It's honestly like a massive, high-stakes puzzle. You have to consider population growth, environmental hazards, existing infrastructure, protected natural resources, the whole shebang. You really can't just guess. You need precise, actionable intelligence. And solving this mystery, well, it requires powerful tools that can visualize and analyze thousands of data points at once. Section 1, Maps and Mapping Basics. Before we start looking at the Earth from space, we gotta understand the fundamental building blocks. For centuries, planners relied on good old paper mapping, but man, it was tedious. The maps were so voluminous, you practically needed a warehouse just to store a single city's plans. And if a new road was built, you literally had to pull out the eraser and manually revise the drafting paper. Doing complex analysis was expensive and, honestly, incredibly time-consuming. But then, enter digital mapping. It's a total game changer. Instead of giant, unwieldy paper rolls, you have a sleek digital database. This means quick retrieval, automatic updates, and lightning-fast systematic overlays. Section 2, Applications of GIS. That digital transformation perfectly sets the stage for our superhero tool that manages all this digital data. Now, GIS isn't just some piece of software you download onto your laptop. It's a complete ecosystem built on 5 cornerstones. Right, so you absolutely need the software to process the data and the hardware to run it. You need the data itself for sure, and specific methods for analysis. But crucially, and what's really interesting about this is you need people. You need trained individuals and organizations who can actually manage the data and interpret the results to make real-world decisions. So let's define exactly what this system actually does. At its core, a geographic information system is a tool to link features with a geographic location. We call this spatial data, basically answering the question, where is it? And it links that spatial data together with other types of information, like tables and statistics. We call that attribute data, which answers what is it. Essentially, it takes the physical geometry of the real world and connects it directly to a deep database of facts. And this brilliantly illustrates how that connection works in practice. A single row of data, say a record showing a 252-hectare residential area, is linked directly to a specific geographic polygon on the map. Because of this link, planners can perform really complex needs analyses. For instance, by mapping out public schools and linking them to attribute data, like student classroom ratios or building conditions, planners can instantly visualize exactly which neighborhoods are overcrowded or in need of immediate repair. Section 3, Map Overlay Analysis. This ability to link and analyze data brings us to one of the most powerful functions of GIS. Think of this like taking multiple transparent maps, each showing different info, like roads on one sheet, rivers on another, and soil types on a third, and stacking them on top of each other on a light table to see how everything interacts. So, if a municipality wants to find the exact areas suitable for development, they use map overlay analysis in a process called simple land accounting. It's basically a method of systematic subtraction. Here's how it works. Step 1, start with the total land area of the city. Step 2, overlay and subtract hazardous areas, things like flood zones, landslide risks, or fault lines. Step 3, subtract areas that are already built up alongside environmentally protected zones that legally just cannot be touched. And Step 4, the result. You're left with the exact areas that are safe, available, and completely suitable for future urban expansion. Now, this subtraction process is actually a form of spatial modeling known as coincidence modeling. So the crucial point is that planners use GIS overlay functions to find the exact places where different values coincide. You're essentially asking the computer, hey, show me every piece of land that is not hazardous and is not protected and is not currently built up. The areas where all those specific conditions coincide become your absolute prime real estate. Section 4, Applications of remote sensing. We've mapped out the ground, so now it's time to zoom all the way out. So what exactly is remote sensing? Well, it's the use of satellite imagery to detect the physical characteristics of the Earth, monitor landscape dynamics, and perform change detection. Its ultimate superpower is looking at an area from space over a specific time interval and identifying exactly where and how the environment has changed. And the best part? It does all this without the massive cost of sending physical survey teams on the ground. Now, when working with satellite data, we have to make a very important distinction: land cover versus land use. Land cover is the physical condition of the ground surface. It's what the satellite actually sees, like a forest, grass, or concrete pavement. Land use, on the other hand, reflects human activity and the functional role of that land. So a patch of grass is the land cover, but its land use might be a residential backyard, a public park, or even a golf course. Remote sensing provides the cover data, which we then combine with GIS to infer the actual use. Let's look at a fascinating real-world case study to see just how valuable this is. Researchers used digital change detection techniques on satellite imagery to study the Hawal Bog block in the Almora district of Uttarakhand, India. They looked at a 20-year period, comparing Landsat satellite images from 1990 all the way to 2010. This allowed them to track the landscape dynamics over 2 full decades. And here are the results of that remote sensing analysis. Over those 20 years, vegetation actually increased by 3.51%. Built-up land, meaning human settlements and urban expansion, also increased by 3.55%. Meanwhile, barren land decreased by a pretty significant 5.46%. This right here is the real-world value of remote sensing. It proves that we don't have to just guess how a region is evolving. We have empirical, visual evidence of environmental shifts. This allows planners to actively monitor land use driven by an increasing population and really adjust their sustainable management strategies accordingly. So, we've seen how GIS links data to geography, how map overlays find the absolute perfect spots for expansion, and how remote sensing tracks a changing landscape from space. So I'm going to leave you with this thought. Based on the planning decisions being made today, how will your own neighborhood look from space 20 years from now? Will vegetation increase? Will built-up land expand? Thanks to these incredible tools, we don't just have to wait and see, we can actively shape that future. Thank you so much for joining me on this explainer.